Hello everyone, this lesson is about internal resistance. From this lesson you'll be able to define EMF, define terminal potential, rearrange EMF equations to show loss volts and find internal resistance. Recap of our definition of EMF. The full name is electromotive force. It's very often given the symbol epsilon. The EMF is the energy available per coulomb of charge. So it's the total energy a cell or other power source supplies to each coulomb of charge. In series circuits, we know that epsilon, the EMF, is equal to the sum of the PDs across each of the components. So epsilon equals V1 plus V2 plus V3, and this comes from conservation of energy, where we know energy cannot be created or destroyed. So most power sources have some internal resistance. It's a resistance which is inside the power supply due to the mechanism of the power supply. And because of this internal resistance, some energy is lost due to the power supply becoming hotter. We can consider that the cell has its own resistor inside, given the letter little r. And that helps us then to visualize what's happening. It also allows us to see what the effect of that is going to be when it's in a circuit combined with a load resistance, big R. So the total EMF, the EMF of the cell is the total energy that can be supplied. If there's some energy lost inside the cell, then to find out the energy that's available to the circuit, we'd need to subtract that from the EMF. And so what we get is an equation which shows us the EMF, the total energy per unit charge available, is equal to the potential difference drop across the cell plus the potential difference drop across the load resistor. And you can see labelled on the diagram there, we've got a current I flowing around the circuit. So that gives us I little r dropped across the internal resistor, and I big R, the potential difference drop across the load resistor. The potential difference across the cell, I little r, is sometimes referred to as lost volts. It's a voltage drop inside the cell due to the cell itself, so it's not available to be applied across the circuit. And what's left is the potential difference across the circuit, which is called the terminal PD, and that's I big R. So it's the current multiplied by the load resistance. So if you could make a note of this equation and just be clear what each term means. This equation can be rearranged to give V equals epsilon minus IR. And in words, that's terminal potential difference is equal to the EMF minus the lost volts inside the cell. Let's look at a worked example. A power supply with EMF 12.0 volts and internal resistance of 0.03 ohms operates a motor with a load resistance of 1.50 ohms. What is the current in the circuit? What are the lost volts and the terminal potential difference? Pause the video and have a go at doing that. So to find the current, we're going to use EMF divided by total resistance. Total resistance is going to be the sum of the internal resistor and the load resistor. So it's 0.03 ohms plus 1.5 ohms equals 1.53 ohms. And so the current is 12 volts divided by 1.53 ohms, which is 7.84 amps. Now we know the current flowing in the circuit, we can find the potential drop across the cell. So it's going to be using V equals I times little r. So it's 7.84 amps multiplied by 0.03 ohms, which equals 0.24 volts. And again, we can use V equals I times R, but this time big R, to find the potential difference across the load resistor, which is our terminal PD. So it's 7.84 amps times 1.50 ohms, equals 11.76 volts. The other way of doing that is we know we've got an EMF of 12 volts. We're dropping 0.24 volts across the resistance of the cell. So what's left? And it's basically what's left is the terminal potential difference. So it's 12 minus 0.24 equals 11.76 volts. I'd now like you to try a couple of questions. So for each one, I'd like you to pause the video, have a go at it, show all of your working, and then you can self-mark. First question, a 1.5 volt cell is connected across a 3 ohm load resistor. Calculate the internal resistance of the cell if a current of 0.4 amps flows. I would suggest drawing the circuit diagram to include the internal resistor and the load resistance as well, and mark on the EMF of the cell and the current. So from this question, the EMF is 1.5 volts, the load resistor is 3 ohms, so R, big R, is 3 ohms. We're asked to calculate the internal resistance, so that's little r, of the cell if a current of 0.4 amps flows, so we're given I. So if we start with the equation, EMF epsilon equals I, big R, plus I, little r. Put the values in, 1.5 equals brackets 0.4 times 3 plus 0.4 times little r. That gives us 1.5, take away 1.2 is equal to 0.4 r. R equals 0.3 divided by 0.4, which equals 0.75 ohms. So we've been able to calculate the internal resistance of the cell from the values given using the equation. Check your working. If you need to study that carefully, pause the video again and make sure you've got how to do that. Next question, the cell has an internal resistance of 1 ohm. Calculate the voltmeter reading across the 20 ohm load resistor. So we can redraw the circuit to show the internal resistance of the cell. And it's handy to think of that as being a resistor. Although it's not actually a resistor component, it's just helpful to visualize what's happening. And if we need to find total resistance, we can see that we would need to add it to the load resistor in the circuit. So we've got an internal resistance of 1 ohm, little r. We've got a load resistance of 20 ohms, and we've got an EMF of 12 volts. So the first thing is to find the circuit current, and we find that from the EMF divided by the total resistance of the circuit. So that's 12 divided by 20 plus 1 equals 12 divided by 21, which equals 0.57 amps. The voltmeter reading will be equal to I times R, load resistance R, which is 0.57 times 20, which equals 11.4 volts. We're not asked this, but we could also show that 0.6 volts is lost across the cell. If the EMF of the cell is 12 volts, and we've got 11.4 volts on the voltmeter, then our lost volts there is 0.6 volts. We know that the sum of the potential differences must equal the EMF. 11.4 plus 0.6 equals 12. We're now going to think about two situations, special cases if you like, where we have an open circuit and where we have a short circuit. So what do we mean by open circuit? So where there's no connection, or where only a very high resistance voltmeter is connected. What would happen to the current and what would happen to the EMF? And where there's a short circuit, so that means that the power supply is connected with wires only, but no components. That's called a short circuit, where there's basically no resistance, no load resistance. In the first situation, open circuit, there's no connection or very high resistance voltmeter, so no current flows. And from our equation, the EMF must be equal to V, because the current is 0, and so I times little r equals 0. of measuring the EMF of a cell. We can literally just connect a voltmeter across the terminals of the cell, and the reading on the voltmeter will be equal to the EMF of the cell. In the short circuit situation, the load resistance is going to be equal to 0. So big R equals 0. So I times big R equals 0. V equals IR, so V equals 0. So there's 0 terminal potential difference. And then if we look at the equation, the EMF must equal I times little r, because V goes to 0. And so therefore, I, the current, is equal to the EMF divided by the internal resistance of the cell. So how would we actually go about finding the internal resistance of a cell? In an investigation, you can only measure potential difference and current. So what we would have is a load resistor in the circuit, which we would vary. And by varying that, we would get different values of current and potential difference across the cell, which is our V, terminal potential. And then we could plot V against I. What we'd find is that we get a straight line with a negative gradient. I'd like you to try and work out what the y-intercept would be, what the x-intercept would be, and what the gradient would be equal to. If you look on the left here, we've got something which is designed to help you here. You can see from this how we are using y equals mx plus c for this particular equation. So the equation is rearranged to give v equals minus r times I plus epsilon. And that's now in the form of y equals mx plus c. So you should be able to see from that what the y-intercept is, the x-intercept, and what the gradient will be equal to. So we find that the y-intercept is equal to epsilon, because that's our plus c here in the equation. The x-intercept is going to be equal to epsilon divided by r. So this is when v goes to 0. So if v goes to 0 in this equation, then epsilon is equal to I times r. So I is equal to epsilon divided by r. And the gradient is going to be minus the internal resistance. The internal resistance is going to be a positive value. So this makes sense because we've got a negative gradient. We just need to reverse the sign and make that into a positive value for the internal resistance of the cell. So internal resistance is an important consideration when considering how much power a circuit can transfer. And what's found is when the load resistance is equal to the internal resistance of the power supply, we actually get maximum power transfer to the circuit. And this can be important in a number of applications. So you can see from the graph we've got power on the y and load resistance on the x. As load resistance is increased from 0, the power transfer increases from 0 to a maximum, and that maximum is where the load resistance is equal to the internal resistance of the cell. And then beyond that, as load resistance increases, the power decreases back down to 0. So we're going to test this idea. This idea is called impedance matching. We're going to test this idea with just looking at some values for a circuit ourselves to see if it works. So testing the idea of maximum power transfer. We've got a cell with an EMF of 1.5 volts and an internal resistance of 2 ohms. Calculate the power transfer, which is going to be found from V times I, where V is the potential difference across the load resistor, sometimes known as the terminal potential difference in our equations. Calculate the power transfer when R, the load resistor R, is equal to 1 ohm when it's equal to 2 ohms and when it's equal to 3 ohms. I'd like you to pause the video and spend a few minutes working on this. So when R equals 1 ohm, the current in the circuit is equal to the EMF divided by the total resistance. So it's 1.5 divided by 1 plus 2, which is 3, which equals 0.5 amps. The terminal potential difference V is equal to I times big R, which equals 0.5 times 1 ohm, which equals 0.5 volts. So the power transfer to the circuit is equal to I times V. So it's 0.5 times 0.5, which equals 0.25 watts. We do a similar thing with the 2 ohm resistor. You can see the working here. And we find that the power transferred is 0.28 watts, so that's higher. And then we do the same thing with the 3 ohm resistor, so it's over on the left, bottom left here, blue writing, and we get 0.27 watts. So we can see that the highest power transfer is when the load resistor is 2 ohms, and that's equal to the internal resistance of the cell. As the load resistor gets bigger or smaller from that internal resistance value, the power transfer reduces. We can see that when the load resistance equals the internal resistance, we get maximum power transfer. So now I'd like you to read carefully through the learning outcomes for this lesson and just make sure you've got everything. And if there's anything you need to go back to, then please do spend some time doing that. So we should know that all power supplies have some internal resistance. So some energy supplied to each coulomb of charge is lost due to heating within the power supply. The EMF is equal to the terminal voltage plus the lost volts, and there are different ways of expressing that as shown here. When I equals 0, then the EMF is equal to the terminal potential difference. So that's a very high resistance circuit or an open circuit. When V equals 0, so this will be a short circuit, the current is equal to EMF divided by internal resistance. The best performance of a power supply is obtained when the load resistance is equal to the internal resistance of the cell. This is known as impedance matching.